Welcome to this problem walkthrough on LeetCode problem number 2098, subsequence of size k with the largest even sum. In this session, we'll explore the problem requirements, discuss potential approaches, and break down the solution step by step. Let's dive in. In this problem, you are given an integer array called nums and an integer k. The task is to select a subsequence of size k from this array such that the sum of the selected subsequence is the largest possible even sum. Now, it's important to note that a subsequence is formed by deleting some or no elements from the array without changing the order of the remaining elements. Once you identify this subsequence, you will return its sum if it is even. If it's not possible to form such a subsequence, meaning there's no combination of k elements that results in an even sum, you will return -1. The input includes the array nums, which can contain integers ranging from -10 to the power of 6 to 10 to the power of 6, and the integer k, which specifies the size of the subsequence. The output will simply be an integer, which is either the largest even sum that can be formed or -1 if it's not possible. For example, let's consider the first scenario where nums is 4, 1, 5, 3, 2, and k is 3. Here, the subsequence, 4, 5, 3, gives the sum 4 plus 5 plus 3 is equal to 12, which is even and the largest possible even sum for a subsequence of size 3. So, the output is 12. In the second example, nums is 2, 4, 6, 8, and k is 3. The subsequence, 4, 6, 8, results in a sum of 4 plus 6 plus 8 is equal to 18, which is even and the largest possible sum for this case, so the output is 18. Now, take the third example where nums is 1, 3, 5, 7, and k is 2. Here, no matter which two elements you pick, the sum will always be odd because all the numbers in the array are odd. Therefore, it's impossible to form a subsequence of size 2 with an even sum, and the output is -1. Now, let's look at the constraints and edge cases. The length of the array nums can go up to 10 to the power of 5, and each element in the array can range from -10 to the power of 6 to 10 to the power of 6. The value of k will always be between 1 and the length of nums. For edge cases, consider situations where the array contains only odd numbers. In such cases, it's impossible to form an even sum, so the output will always be -1. Also, if k is equal to the length of nums, you must consider the entire array and check whether the sum of all its elements is even. Additionally, for large input sizes, the solution must be efficient with a time complexity of O, n log n, or better, such as O, n. Finally, negative values in nums can influence the result, so you'll need to carefully select elements to ensure the sum is maximized while maintaining the even property. To approach the problem, we first consider the brute force method. The intuition behind this is straightforward: generate all possible subsequences of size k from the array. For each subsequence, calculate its sum and check if it is even, keeping track of the largest even sum encountered. While this method is simple to implement, it is computationally expensive. Generating all combinations of size k involves choosing k elements from n, which grows exponentially. Additionally, calculating the sum for each subsequence adds further overhead, making the approach infeasible for larger inputs. To address this inefficiency, we explore an optimized approach using a greedy strategy combined with sorting. The idea here is to focus on maximizing the subsequence sum by prioritizing the largest numbers. By sorting the array in descending order, we can easily identify the top k largest numbers. However, since the sum must also be even, we introduce an adjustment step. If the sum of these numbers is odd, we modify the subsequence by swapping one number for another outside the subsequence, ensuring the sum remains even while maintaining the size of the subsequence. This adjustment step is critical to the optimized approach. After computing the sum of the top k numbers, if the sum is odd, we look for the smallest odd number in the subsequence and attempt to replace it with the smallest even number outside the subsequence. Alternatively, if no such replacement is possible, we can swap the smallest even number in the subsequence with the smallest odd number outside. This ensures that the resulting sum is even. The overall complexity of this approach is dominated by the sorting step, which takes O, n log n. Selecting the top k numbers is linear in k, and finding the smallest odd or even numbers for the adjustment requires scanning the array, which is linear in n. Thus, the total complexity is O, n log n, making this method significantly faster than brute force. However, it is important to handle edge cases carefully, such as when no valid adjustments are possible. Another alternative involves using heaps, which can streamline the process of managing the largest and smallest numbers. By maintaining a max heap for the top k numbers and min heaps for odd and even numbers outside the subsequence, we can adjust the sum more efficiently. This approach avoids the need to sort the entire array but introduces additional complexity in managing multiple data structures. Ultimately, the optimized approach with sorting was chosen as the solution for its balance of simplicity and efficiency. Sorting the array allows us to quickly identify the largest numbers, while the adjustment step ensures the even sum constraint is satisfied. The overall complexity of O, n log n, is manageable, and the approach is straightforward to implement and debug. The decision was guided by key observations. First, the largest sum can only be achieved by including the largest numbers in the array. Second, ensuring an even sum requires minimal adjustment, which can be handled effectively after sorting. And third, sorting is a universally applicable technique that simplifies the implementation. While the heap-based approach offers comparable complexity, it adds unnecessary complication with additional data structures. The brute force method was ruled out due to its prohibitively high computational cost, making it impractical for larger inputs. By choosing the optimized approach, we strike a good balance between efficiency and simplicity, ensuring the solution is both performant and easy to understand. The problem asks us to find the maximum even sum of any subsequence of size k from the given array nums. If it's not possible to form such a subsequence, we should return -1. To tackle this, we start by validating the input and handling edge cases. For example, if the array length n is less than k, forming a subsequence of size k is impossible, so we return -1 immediately. Additionally, if k equals the array length, we simply sum all elements in the array. If this sum is even, we return it, otherwise, we return -1. Next, we separate the numbers in nums into two lists, one for even numbers and another for odd numbers. This separation helps us handle the even sum property later. Sorting both lists in descending order allows us to easily pick the largest numbers, which is critical for maximizing the sum. To generate candidate subsequences of size k, we initialize a variable max_even_sum to -1, which will store the largest even sum we find. The key idea here is to iterate through all possible counts of even numbers, called even_count, that could be included in the subsequence. The count of odd numbers, odd_count, is simply k even_count. However, we must ensure that both even_count and odd_count are valid, meaning there are enough numbers in their respective lists to pick from. For each valid combination, we construct a candidate subsequence by selecting the largest even_count numbers from the evens list and the largest odd_count numbers from the odds list. We then compute the sum of this subsequence. If the sum is even and greater than the current max_even_sum, we update max_even_sum. Finally, after exploring all possibilities, we return the value of max_even_sum. There are several key insights that make this algorithm efficient and effective. First, the property of even sums is crucial. A sum is even only if the count of odd numbers in the sum is even. This means we should prioritize selecting odd numbers in pairs. Second, sorting the evens and odds in descending order ensures that we always start by picking the largest numbers, which is essential for maximizing the sum. Third, the range of even_count is carefully chosen to include only valid combinations of even and odd numbers that sum to k. Finally, handling edge cases like k greater than n or k equals n early in the process allows us to simplify the core algorithm and avoid unnecessary calculations. From a data structures perspective, we use two lists to store even and odd numbers separately, and a single variable max_even_sum to track the result. Sorting these lists upfront enables efficient selection, ensuring the algorithm performs well. Analyzing the complexity of the algorithm, we can see that the most computationally expensive step is sorting the evens and odds lists, which takes n log n. Separating the numbers into these two lists requires a single traversal of the array, which is n. Iterating through the combinations of even_count and odd_count involves additional computations, but since the dominant factor is the sorting step, the overall time complexity is n log n. As for space complexity, we use additional space to store the evens and odds lists, which together require n space. No other significant data structures are used, so the total space complexity is also O(n). This balance of time and space efficiency makes the algorithm well-suited for handling reasonably large inputs. Let's walk through an example to solidify our understanding. Given the input nums equals 4, 3, 6, 7, 2, 5, and k equals 3, we first separate the numbers into evens equals 4, 6, 2, and odds equals 3, 7, 5. Sorting these lists gives evens equals 6, 4, 2, and odds equals 7, 5, 3. Now, we iterate through possible values of even underscore count. For even underscore count equals 0, we select 3 odds, 7, 5, 3, resulting in a sum of 15, which is odd, so we skip this case. For even underscore count equals 1, we pick 1 even, 6, and 2 odds, 7, 5. This gives a sum of 18, which is even, so we update max underscore even underscore sum to 18. For even underscore count equals 2, we select 2 evens, 6, 4, and 1 odd, 7. The sum is 17, which is odd, so we skip it. Finally, for even underscore count equals 3, we select all 3 evens, 6, 4, 2, resulting in a sum of 12, which is even but less than 18. Thus, the final result is max underscore even underscore sum equals 18. Here, we start by defining a class called solution and its method largest even sum. The input parameters are the array nums and the integer k. First, the array is sorted in descending order to prioritize the largest elements, making it easier to select the largest subsequence later. Then, we separate the elements into 2 lists, evens for even numbers and odds for odd numbers. This distinction is important because the sum of the subsequence must be even. Next, we add a condition to check if the combined count of evens and odds is less than k. If it is, it's impossible to form a subsequence of size k, so we return -1. After that, we select the first k elements from the sorted nums array as our initial candidates for the subsequence and calculate their sum. If the sum of these k elements is already even, we can directly return it. However, if the sum is odd, we need to adjust it to make it even by swapping elements inside and outside the candidates list. To adjust the sum, we need to identify the smallest odd number within the candidates and the smallest even number outside the candidates. Similarly, we find the smallest even number in the candidates and the smallest odd number outside the candidates. These values allow us to calculate the possible adjustments needed to make the sum even. Specifically, we consider 2 scenarios: replacing the smallest odd number in the candidates with the smallest even number outside, or replacing the smallest even number in the candidates with the smallest odd number outside. Both adjustments are added to an options list if they are valid. Finally, we return the maximum even sum from the options list. If no valid adjustment exists, the method returns -1, indicating that no even sum of size k is possible. Here, we start by importing the necessary utilities and defining our solution class. The main method, largest even sum, takes an array of integers and a number k, representing the size of the subsequence we need to form. The first step is to sort the array in descending order, which we achieve by sorting it in ascending order using arrays.sort and then reversing it with the helper method reverse. Sorting ensures that we can easily pick the largest numbers for maximizing the sum. Next, we separate the numbers into 2 lists, evens for even numbers and odds for odd numbers. This categorization will help us later when we try to adjust the sum to ensure it is even. Before proceeding, we perform a quick validation. If the total number of elements in both lists is less than k, it's impossible to form a subsequence of size k, so we return -1. Finally, we prepare to pick the first k elements, which are the largest numbers in the array after sorting, as our initial candidates for the subsequence. We initialize the variable current sum to keep track of the total sum of our selected candidates and use a list named candidates to store these elements. A loop runs k times to pick the first k largest numbers from the sorted array, adding each number to both the candidates list and the current sum. Once we have our initial subsequence, we check if the sum is already even. If it is, we directly return current sum since our goal is met. However, if the sum is odd, we need to adjust it. To do this, we identify the smallest odd and even numbers both inside and outside the candidates list. These values will help us make the necessary adjustments. To start, we initialize smallest odd in candidates, smallest even in candidates, smallest odd outside candidates, and smallest even outside candidates to integer.max_value, which represents the largest possible integer value. Then we iterate over the candidates list, updating the smallest odd and even numbers within the subsequence. This prepares us to later swap elements to achieve the desired even sum. We now focus on the elements outside the candidates list, iterating through the remaining numbers in the array starting from index k. Here, we look for the smallest odd and even numbers that are not part of the current subsequence. These values are stored in smallest odd outside candidates and smallest even outside candidates, respectively. With these smallest values identified, both inside and outside the candidates list, we calculate two possible adjustments. The first option, option 1, involves replacing the smallest odd number in the candidates with the smallest even number from outside. Similarly, the second option, option 2, involves replacing the smallest even number in the candidates with the smallest odd number from outside. Each of these adjustments is only valid if the respective values exist, meaning they are not equal to integer.max_value. Once we have the potential adjustments, we compare their results using math.max to return the largest valid even sum. If neither adjustment is possible, we return -1, indicating that no valid even sum can be achieved. Finally, we define the helper method reverse, which is used to reverse the order of the sorted array. This method takes the array as input and swaps elements symmetrically from the start and end indices, progressively moving towards the center. By doing this, we transform the array into descending order after it was initially sorted in ascending order. The method uses a temporary variable to hold one of the values during the swap, ensuring that the elements are correctly exchanged. Once the reversal is complete, our array is ready for subsequent processing in the rest of the solution. With this, the implementation is complete, and the method is capable of determining the largest even sum of a subsequence of size k. To solve this problem, we start by examining the first example. The input array is nums equals 4, 1, 2, 3, 7, and we need to form a subsequence of size k equals 3 with the largest even sum. First, we sort nums in descending order, resulting in nums equals 7, 4, 3, 2, 1. Next, we separate the numbers into even and odd groups. Here, the even numbers are evens equals 4, 2, and the odd numbers are odds equals 7, 3, 1. We then check if the total number of elements is sufficient to form a subsequence of size k. Since the combined length of evens and odds is 5, which is greater than or equal to k, we can proceed. Now, we select the first k elements from the sorted array as candidates, giving us candidates equals 7, 4, 3. Adding these numbers together, we calculate the sum as current_sum equals 7 plus 4 plus 3 equals 14. Finally, we check if this sum is even. Since 14% 2 equals 0, the sum is even, and we return 14 as the result. In the second example, the input array is nums equals 1, 3, 5, 7, 8, and we again need a subsequence of size k equals 3 with the largest even sum. We start by sorting nums in descending order, resulting in nums equals 8, 7, 5, 3, 1. Then, we separate the even and odd numbers. Here, the even numbers are evens equals 8, and the odd numbers are odds equals 7, 5, 3, 1. We check whether the total number of elements is sufficient to create a subsequence of size k. Since the combined length is 5, which is sufficient, we proceed by selecting the first k elements from the sorted array. This gives us candidates equals 8, 7, 5. Next, we compute their sum, which is current_sum equals 8 plus 7 plus 5 equals 20. After calculating the sum of the selected candidates in the second example, we check if the sum is even. Since 20% 2 equals 0, the sum is even, and we return 20 as the result. Now for the third example, the input array is nums equals 1, 3, 5, and we need a subsequence of size k equals 4. We begin by sorting the array in descending order, resulting in nums equals 5, 3, 1. Separating the numbers into even and odd groups, we find that the even numbers are evens equals, and the odd numbers are odds equals 5, 3, 1. Here, the total number of elements is 3, which is less than k. Since it is not possible to form a subsequence of size k, we return -1 as the output. To analyze the time complexity, we break down the solution into its main operations. First, the array nums is sorted in descending order. Sorting an array of length n requires n*log n time. Once sorted, we use a list comprehension to separate even and odd elements by iterating through the array, which takes n. These two steps are independent of each other. Next, we check if there are enough elements to form a subsequence of size k. This step involves a simple comparison of lengths, which is a constant time operation, O1. After this, we select the first k elements from the sorted array. Slicing these elements takes k, and calculating their sum also requires k. Finally, the solution calculates adjustments by identifying the smallest odd or even elements inside and outside the selected k elements. These operations involve iterating through at most k elements for the candidates and at most n k elements for the outsiders. In the worst case, each minimum operation takes n, but overall, these steps remain efficient. The final adjustment step involves evaluating the options for modifying the sum to ensure it is even. This requires a constant number of operations, making it 1. When we combine all these steps, the dominant factor in the time complexity remains the sorting operation, which is n*log en. Subsequent operations, such as separating elements, slicing, summing, and finding adjustments, are linear or sublinear in nature. Therefore, the overall time complexity of the solution is n*log n. Now, let's look at the space complexity. First, the input array nums occupies n space. Additionally, the solution uses auxiliary lists, evens and odds, to store subsets of the input array. In the worst case, one of these lists could contain all n elements, while the other remains empty, resulting in n space usage for these lists. Finally, intermediate variables like candidates, current_sum, and adjustment options require at most k, or constant space, which is negligible compared to the n required for the input and auxiliary lists. When we consider the overall space complexity, the solution does not utilize any additional data structures beyond the input array and the auxiliary lists evens and odds. Therefore, the overall space complexity is n. To put this into perspective, let's compare the optimized approach with a brute force method. A naive approach would involve generating all possible subsequences of size k, calculating their sums, and checking for the largest even sum. Generating all possible subsequences of size k from an array of length n would take 2 to the power of n, and checking each subsequence for its sum and parity would require k. This results in an overall time complexity of 2 to the power of n*k, which is exponentially worse than the optimized solution's n*log n, especially for larger input sizes. The optimized solution significantly reduces computational overhead by leveraging sorting and selective adjustments. Sorting the array ensures that we can focus on the most promising candidates for the subsequence, while adjustments are made efficiently. This brings the time complexity down to n*log n. Space usage is also efficient, requiring only n for auxiliary lists and negligible additional memory. When analyzing the best, average, and worst-case scenarios, the best case occurs when the sum of the first k elements is already even, allowing us to directly return the result. Here, the complexity is dominated by sorting, which is n*log n, with summation contributing an additional k. In average and worst cases, adjustments to the sum may be needed, but these adjustments involve linear scans, keeping the dominant factor as n*log n. Mathematically, sorting dominates over all other operations, and space usage is proportional to the input size. Thus, the overall complexities of the solution are confirmed as n*log n for time and n for space. Here are some common mistakes you might encounter when solving this problem. First, forgetting to handle edge cases can lead to runtime errors or incorrect outputs. For example, if the array has fewer than k elements or if all the numbers in the array are odd, your solution needs to account for these situations explicitly. Another mistake is implementing an inefficient brute force approach. Generating all possible subsequences of size k without filtering out invalid candidates early can quickly cause your solution to slow down, especially for larger inputs, due to the combinatorial explosion in runtime. Misunderstanding the calculation of an even sum is also a frequent issue. Remember, not every combination of numbers will result in an even sum. For instance, any odd-length subsequence consisting entirely of odd numbers will always produce an odd sum. Overcomplicating the solution is another potential pitfall. Using excessive data structures to store all subsequences or sums increases space complexity unnecessarily. Instead, focus on keeping track of just the maximum even sum. Finally, be cautious about relying too heavily on sorting. While sorting can be useful in certain cases, it's not a universal solution, especially if the order of numbers within the subsequence affects the result. Now, let's discuss some insights that are particularly useful in interviews. A key pattern to remember is that a sequence's sum is even if and only if there is an even number of odd numbers in the subsequence. This property can help you eliminate invalid candidates early in your solution. To approach the problem optimally, combine greedy strategies with mathematical properties like parity checks to efficiently identify the largest even sum. Avoid the temptation to generate all possible subsequences, as this is computationally expensive. It's also important to explain trade-offs during an interview. For instance, while a brute force approach can be helpful for understanding the problem, it becomes impractical as the input size grows. Highlight how optimized methods significantly reduce both time and space complexity. Additionally, clear communication is key. Make sure to clarify edge cases, such as when the input array is empty or contains no even numbers. Demonstrating awareness of constraints and edge cases can make a strong impression during an interview. Finally, let's take a look at related problems and alternative approaches. Problems like LeetCode 78, subsets, and LeetCode 90, subsets 2, can help you practice generating all subsequences, including handling duplicates. LeetCode 416, partition equals subset sum, focuses on understanding some properties in subset generation, which is directly relevant here. Similarly, LeetCode 198, house robber, is a great way to practice dynamic programming with non-contiguous element selection. When considering alternative approaches, a greedy method can be effective. For example, you could start by identifying the largest k numbers and checking if their sum is even. If it's not, you can try swapping numbers to maximize the sum while ensuring it remains even. However, this approach may not work for all constraints. Dynamic programming is another option, where you use a table to track the maximum sum achievable for each subset size and parity. This ensures thorough consideration of all possible sums while maintaining efficiency. Lastly, a sorting-based approach combined with two pointers can be useful if the problem allows sorting. This technique involves including or excluding numbers to achieve the desired parity and maximize the sum, typically with better performance than brute force. Great job! We've wrapped up our discussion on this problem. We covered the key points, approaches, and takeaways, and I hope you found this walkthrough helpful. Don't forget to practice similar problems and apply these concepts in your next coding challenge. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!